The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, welcome back, everybody. First of all, I want to apologize to the virtual world out there that we didn't get last lecture on tape. So I want to do a quick recap. Honestly, I mean no more than 2 or 3 minutes on what happened. And that's why I put all the effort in putting it up on the board first. So remember, we're dealing with a formal system here. And here I'm just going to denote this formal system as F. Recently, we've been interested in typographical number theory, TNT. And we carried out this process of encoding symbols of F through this Gödel numbering process, essentially giving equals, a number like 555 and things like this. So we have now symbols of F corresponding to a small subset of all natural numbers. We then have this correspondence, this actually exact mathematically precise isomorphism between strings of F and subset of all numbers, which is the Gödel number of some string, the strings that we have over there. We then take our rules, axioms and rules of F. Remember, these were formal recursive operations on strings in our formal system. And we arithmetized them. We said, OK, we're going to let the process of induction be equivalent to taking 10 times blah, 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 this number, blah, 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 divide by, blah, 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 Chinese remainder theorem, blah, blah, blah. And we're going to actually be able to do the same symbol shunting we would do with like the MIU system or with the typographical number theory system, and just do it in the form of numbers. And this is why, with Gödel's incompleteness theorem, we need formal systems strong enough that encompass number theory in order to do this process. So we then have strings which are statements of F, which correspond to numbers that are F producible. We then kind of do this leap outside of the system. We have meta F, right? And we're taking statements about strings of our formal system. And this corresponds to number theory, taking statements about numbers which are F producible, right? Which are F numbers. And an example of this was, in number theory, we say, OK, so 641 is prime, or 6 is a perfect number. And we just denote this property, perfect number. And we can make it a property with a free variable. And we say, all right, is 5 a perfect number? No. Is 6 a perfect number? Yes. And we can create a new property called primness, which corresponds to provability. And then we essentially then have this problem of determining whether a particular string is a theorem of F is equivalent to establishing whether or not a number is prim. So I wanted to quickly recap, going back over here, so the essential steps in Gödel's proof. So we arithmetize. Just take that as is. Arithmetize. We give symbols numbers, and we give rules for inference and deduction operations on numbers. So then we make this property of provability, and we equate it through this exact precise isomorphism which Gödel discovered to a property of primness. We then turn the operation of quining. So quining was, when preceded by itself in quotations yields a full sentence. Of course, we could play around with this. Like, so snow is white didn't mean anything. But when we fed that operation, that function itself, into that variable for when preceded by itself in quotations yields a full sentence, when preceded by itself in quotations yields a full sentence, created a full sentence, which was itself self-referential. And it was a fixed point, which, remember, is when you have a function, which was, in our case, a property of quining, or it could have been just simply like multiplying by 2x. A fixed point is something which, when you feed it into your function, you get the same thing back out. So we took quining into an operation on numbers. Our fixed point of quining gave us an inherently self-referential sentence. And then we were able to describe, not directly spell out, but describe a formula which felt like this statement here. When fed its own Gödel number yields a non-prim number. When fed its own Gödel number yields a non-prim number, which describes this big thing called G. And G is essentially the reason why number theory is incomplete. It's what breaks the mathematician's credo, this idea of true if and only if provable. And with the production of G, we were able to establish that although all provable things are true, not necessarily all true things are provable. And this was a very important idea. It's the take-home message of the course. We connected this briefly to the halting problem, which is just this idea of you can't have a magical machine which you can take in a program and an input, and it'll tell you whether or not it'll terminate. Just like you can't have a magical machine which says, give me the Gödel number for some statement in number theory, and I'll tell you whether or not it's true or false just by detecting whether or not it's prim or not prim. These things are inherently impossible and undecidable, and this was kind of the shaking of the foundations of number theory, which we wanted to do. But that's all I wanted to say about this. I wanted us to move on and now think about more enjoyable things, because number theory, great. I wanted more just the take-home message of this idea of having things which are true but not within our system, right? And the idea that we have to jump outside the system. Yes, Latif?
Can we do like something we can have like our formal system? Then we get all the Gödel statements, and then get formal systems in which those holds. And so by doing that, we generate more formal system and then get like their true statements, statements about them that are false in that system for it to be consistent. Do this for all the systems we can come up with. Can we like by that way like create all the mathematics there is?
Right. So essentially, this idea of going ahead and giving Gödel numbers for our axioms and our rules of inference, and then just being able to essentially generate all of mathematics by just feeding it to a computer and let it carry out these operations on numbers, right? So we could produce a computer which would produce provable things in that direct fashion, but it'd be incredibly inefficient, right? Like one of the remarkable things about humans and the human intellect is that we're able to essentially jump several nodes down the tree and not work. We don't think on the level of formal deductions on operations of symbols, right? And also, once again, like that's the whole point of Gödel's incompleteness theorem, is that we can't produce all mathematics.
Yeah, I know you can't, but you can like certainly try to like derive like statements that are almost similar to what it says, and then get systems in which those statements, which are false in some other system, hold for that system, and then try to explore that other system to see which mathematics it gives you.
Okay, so is the idea then that we essentially take our G here and we let that be essentially an axiom of a new system, and then
we just like get a system in which that thing can be derived to be true.
All right,
and
so
to be speaking about another system, but not the system which
right, exactly. So essentially, we would have to. It's almost trying to like make our system complete by considering a system where G is derivable, right? Exactly. So no, I mean that's totally key, and mathematicians gave exactly the same point after Gödel did this. But what Gödel showed is that even if you were to tack on G as part of your new system, you could then create an analogous G prime, which was incomplete in that system.
I know that that's the problem. But since there's a lot of these like incompleteness things all over mathematics, if we can just find them and create new systems that like sort of support them, then we can like have like other mathematics that are not covered by the other system. So it's just like a way of exploring the
right.
mathematical landscape.
Well, no, I mean, yeah, we're doing that all the time, right? Like, but it's not necessarily that we can just start out and somehow get the complement of provable of not provable statements very easily. Like, I mean, that's essentially what mathematicians do. That's why mathematicians never go out of a job, is that we fundamentally need to think about and create new concepts and make new definitions, and then explore the deductions of our new assumptions and axioms, which weren't covered by the old, system involving number theory. We need to add new stuff on there that can't be done in a mechanical process. It requires human intelligence. But I mean, that's good. Like, if you want to talk about this a little more, we should do it after class, because we got a lot to pack in today. But let me know if I haven't answered your question fully. We'll do it afterwards. So I wanted to quickly digress. I kind of take a stand back, right, and say, okay, well, Gödel found this really nice thing. He found this isomorphism, essentially, between PM, Principia Mathematica, and the things it was describing. So he was able to get the system to talk about itself. but I think that always begs the question, was what if he hadn't discovered this isomorphism? What if he hadn't discovered this kind of link, this analogy? And this actually relates to a story that kind of Curran and I have recently. And, you know, Curran was coming up to Boston, and, you know, he says, all right, I'm coming into Kindle soon. I'm like, all right, great. So I kind of jokingly texted back and said, okay, have spacesuit will travel, right? So Curran texts back, he goes, ha ha ha, excellent. So I'm like, okay, great, he got my joke, right? And then I was like, oh, so we met up, and I was like, how'd you like the joke? And he was like, yeah, I thought it was funny. I was like, well, you got the reference, right? And he was like, no, what are you talking about? I'm like, well, Have Spacesuit Will Travel is a book by Robert Heinlein. And he was like, no, I've never heard of it. I just thought you were like putting on this metaphorical spacesuit and that you were going to go meet me at the T, and that's why you could travel, right? And I was like, oh, ha ha ha, I think that's funny that you thought I was funny even though you didn't get my joke. And then so we kind of talked about this for a little while, and he's like, well, so what's the book about? And I was like, actually, I don't know. I haven't read it. So then I Wikipedia'd it today, and I was thinking, well, actually, at the end of the book, the main character gets a full scholarship at MIT. So there was like a third layer of meaning, which neither of us knew. And it was just this level of isomorphism, which we didn't know. But everything seemed to be operating just fine, right? So I think it's kind of interesting. You have this idea that what if we had just gone straight forward with PM without knowing any kind of analogies, this ability for the system to do self-talk? Like, what would have happened? Like, would have mathematics just marched on like fine, thinking it was complete and everything? I just think that's kind of an interesting idea. But I want to give a quick signpost to what's happening today. How many of you guys read Chapter 10, Levels of Description of Computer System? Or at least started to read? Great. Excellent. Fantastic. Nobody read the wrong chapter, which was Chapter 16. That's a good chapter, but it's a little advanced in that it uses a lot of concepts from Chapter 13 and 14, which really help hit home the idea of Gödel's proof. And you should read in your own time. So what I want to talk about today is this concept of emergence and emergent properties coming out of simple descriptions, right? We've been kind of hitting this home all the time, but you know, today's kind of our last day to just really try to show complexity and show how it's emergent out of a simple building items, out of simple building items. Sorry. And really what this chapter here starts with, and why do you think we talk about computer systems? Does anyone have an idea? Did anyone find it interesting? Sandra?
Just like computer systems, we use the same way as like the way we think.
Okay.
Breaking it down.
So we use computers in the same way that we think, like in terms of breaking down.
Yeah, and that's how we can program it and fix it for a logic reason.
Right, exactly. So, go ahead.
So we base it on, so we make computer systems programming programs, so is it based on the way we think, or is it already out there?
Okay.
We just compile it to it.
Ooh, all right, so let me make sure I understand what you're saying. So are you asking, like, are the programs that we program just based on how we think? Like, essentially it's just our idea, hey, we want the computer to do this.
Yeah, and how is it universal?
And how is computation?
Is it
So how is computation kind of universal? Is that what you're getting at? Okay. Yeah, I mean, so that kind of leads back to a fundamental idea of a Turing machine, right? Where you have, although we subjectively have this own approach to how we'd solve the problem, right? It can ultimately be reduced to an algorithm, a set of instructions, which is universal. It's as universal as mathematics, right? So pretty much anybody in any language should understand it, right? Is that kind of what you wanted to say? Okay. Naveen. Oh, sorry. Latif.
Could we just be an implementation of a Turing machine?
Say again?
Could we be just an implementation of a Turing machine?
Could we just be,
Yeah.
like, you know, us as humans be implementations?
Yeah,
of,
and like emotions are like different ways of like talking about like some part of a Turing machine.
Okay. All right. So you're getting at a really interesting idea here. This idea that humans in our thoughts are actually best modeled by a Turing machine, right? And I don't know if you've done this reading, and maybe that's why you're being clever and asking this question. but have you heard of someone named Roger Penrose? Yeah. Okay, so Roger Penrose is a very prominent mathematical physicist. He's at Oxford, right? And he also wrote a pretty interesting book called Shadows of the Mind, in which he suggests that Gödel's incompleteness theorem and the halting problem has application to human intelligence. But what he argues is that humans are fundamentally not Turing machines, but that computers are, right? And that's why artificial intelligence in his mind is impossible, is because a machine is always limited to these kind of constraints, which we've cooked up here today and through the halting problem. But humans obviously aren't. We can meta-think, we can meta-meta-think, and we can meta-meta-meta-think, always jumping outside the system, right? But we're never, ever bound to the same constraints of a machine. Now, I'll warn you, Penrose's ideas are...
Who constrains the machine?
Who constrains the machine?
The ones who program
Logic.
it.
Logic, right? The fact that all a machine can do is, not, and, copy, jump, basic assembly code, right? Right? It is just a Turing machine.
But what can a human do?
What can a human do that's not a Turing machine? Good question, right? We can think emotionally. We can believe, we can double think, right? Humans all the time believe in both P and not P.
Yeah, but it's like, humans aren't like these coherent systems. It's like, I think we think like we're like one thing when we're like really many things. That can also be contradictory. It's like a bunch of little machines going together, like communicating with each other. They can contradict, but they can agree.
Okay, so you've got essentially this kind of society of the mind viewpoint, Marvin Minsky's book, where human intelligence is best modeled by a bunch of little actors, right, that kind of almost vote on certain beliefs, right? And, I mean, it's a good question, right? You also want to have to figure out, one, how do the actors work and how do the actors make decisions? But two, do you really think it's just a majority kind of rules inside your brain? Like, are little guys, little homunculuses up in your head, like, voting on, like, no, I think today we do believe in God, and, no, I don't believe in God, and then, all right, everyone raise your hand if you do, if you don't, okay. Today, we don't believe in God, right? I mean, is that really how human intelligence works, right? We don't know, right? But that's the important thing about studying layers of systems, layers of description, and that's what this chapter is all about. So I'm going to give someone else like an opportunity to explain, essentially, why do we study computer systems and try and understand intelligence, trying to understand the mind? Does anyone have an idea?
Because we can from things that we think we know we can do, we can try to make a computer do similar things in some way, just to maybe suggest maybe this is how we also do the same thing.
Okay. So, possibly, right? I'm not sure. But here's what I kind of came up with, and it's my motivation for why I think people might want to study computer science. This will kind of launch into a whole little lecture of what do you want to do with your life kind of thing. I'm not going to try to solve that problem for you, but we can try. So what I think is cool about computers is that kind of back in the day, if you want to go all the way back to Babbage and these guys in the late 1800s, right? They were just playing around with gears and things like this, right? So I mean, they were working with just physical level, right? So we had kind of this physics governing everything, and he was playing with gears and wheels. But what really makes up today is we have these we have transistors and capacitors. We have electronic things for doing really small kind of computations. Like Babbage was thrilled when he could just get like a simple calculating machine. Like, aha, wow, now you can do logarithms. Like, this is amazing. But he was programming at this level, right? His levels of description were almost completely based on gears, wheels, and then what became in the 1900s, early 1900s, transistors and capacitors. But then we kind of had this, I would suppose, this kind of revolution in how we do things, and we got up to the level of kind of, to speak in modern terms, motherboards and like video cards and things like this. And we went ahead and started like abstracting entire chunks of hardware to do very specific, highly designed things. And we just started playing around with those chunks. Like, aha, now I won't have as much lag in my video games. I can have a new video card and pop that in. So we no longer have, I mean, how many people, I mean, at least popular computer users, ever worry about the transistors and capacitors in their computer? Like, oh no, like, it doesn't happen. And then we have this kind of next step up of, and this is really where the realm of computer science lives, is software and operating systems, which kind of live on top of this even. And this is amazing, right? Like, suddenly we're dealing with things which don't really exist, right? We're kind of executing spells. When Curran gets up later today and he hacks away on his computer, type, 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 he just puts in these little images that show up on the screen, and then he hits an enter button, and then it suddenly like executes like magic, and it exists in a different kind of realm, but it all boils down to what's happening on this level of transistors and capacitors. And the ability to actually tell you, if you went to somebody and you said, hi, my name's X, can you tell me how Windows works in terms of capacitors and transistors, right? They would just kind of go like, do you want to enroll in school for the next 4 years? Like, sure. Like, and that's really the project here. But what's interesting is that there's a conceptual framework we have for thinking here, which is very close to how we hope to crack the problem of the mind. And that's the idea that we kind of have neurons and neurotransmitters, things ultimately govern transmitters. Sorry, ran out of space here. We describe things in terms of like cable theory, like we're just sending messages down an insulated cable. And we have this kind of level of description for the brain at this very small level, and this is already research worthy. But then we have a bunch of biologists and such, and people interested in neuroanatomy, talking about like, oh, what about the amygdala? I don't know if I'm spelling any of this right. But the hippocampus, and your front cortex, your cerebral cortex, and I'll just denote by cortices. I don't know if that's the correct pluralization. And then somehow, out of these larger structures, where you abstract away the details of what's going on with the transcription in this cell, and instead you're just thinking about like, how's my hippocampus doing today? We then all the way enter essentially an isomorphic level of software and OS, which is the psyche, the mind, and I'll go ahead and put it up here, soul, right? And this is kind of fundamentally why artificial intelligence researchers are found in the computer science department. It's because we've had a lot of guys who have gone from this level of dealing with very kind of clunky physics to doing really souped up stuff on like larger physical entities, motherboards, video cards, and then getting up to kind of the level of software systems and operating systems. But I want to take a quick poll. Like, where do your guys' interests lie on this kind of stack? Kind of in both camps here, but especially focusing on the brain and going up to the mind, right? What do you guys find most interesting, right? And this is going to really reveal a lot about who you are and what you want to do, right? What do you find most interesting in these kind of 3 boxes? Like, if you had to vote for one box, what would it be? You want 2 boxes? I can't give you 2 boxes. You got to decide. I mean, otherwise you're going to be in school forever, right? All right, 2 boxes, but that means you automatically have to go to school for 7 years after undergrad, right? Okay, go ahead. Give me some votes. I want to see some hands. Who likes studying molecules, neurons, neurotransmitters, maybe even basic physics? Okay, Sandra, Durs, Maya, Rishi. Okay. who's kind of the inherent biologist here who likes, you know, amygdalas, hippocampus, et cetera, cortices? All right, we got Latif. All right, now who's interested in kind of the psyche, the mind, the soul? Who wants to like kind of actually sit in an office and deal with people's problems rather than, or maybe not. I warn you, it's you don't want to deal. Okay, so we got Naveen. I'm sorry, I forget your name again.
Vivian.
Say again?
Vivian.
Vivian, Maya, Latif, and Felix. Okay, cool.
I have another one to add.
Okay, go for it.
Who wants to understand the commonalities between all of these levels?
Okay, we're getting a lot of hands there. All right, so who wants to understand the commonalities between all these? All right, and this is, you know, Curran and I kind of put together this list, and he'll show you when he kind of comes up and gets the projector rolling. But it's this idea of we've found ourselves working with problems and systems which are so complex that we can only really occupy ourselves with kind of certain layers of abstraction. But the interesting thing is that we can abstract, right? Just like when we're, you know, modding out our computer, like we don't ever have to really care about transistors and capacitors, right? And similarly, when I'm, you know, playing around on MATLAB, right, I don't ever have to worry about like, well, sometimes I have to worry about memory use, but I don't usually have to worry about any physical details. Yes?
You can't have one without the other, right?
Right, exactly. Sandra says you can't have one without the other. Very important, right? Very, very important. Is you do have a tower here, right? But what's scary, maybe scary, is the idea that some of these things are universal and are independent, right? Latif.
You can have the physical things without the soul or the mind or the psyche.
Okay, so definitely, right? These arrows only go one direction. You can have the physical thing without kind of the mental, right? We have plenty of trees and things who don't have Windows Vista running on them. Go ahead.
The arrows represent.
What do the arrows represent? Did you have to ask me that question?
No, but, well, I don't know if it's an arrow, but like, there must be, you know.
All right, so that's actually a very good question. That's a very good question. So what do the arrows mean? So a simple answer would be they indicate, I guess, derivability or dependence, right? Except the dependency is kind of going the other way, right? You know, motherboards and video cards depend upon their underlying transistors, capacitors, but the arrow is kind of pointing up towards them. That's this idea that you can build things out of it, right? And this is an important idea, is that like once you've got a basic amount of tools available to you, you can kind of start building upwards, right? Like once you've got, and this is, I think, very interesting, and it's a good concept to study for kind of languages, right? So when you're learning Spanish or any other language, what's perhaps the most useful phrase that you'll ever learn in Spanish? Okay, hola. Why? Why is that useful? You can say hi, big deal. What if you want to learn more Spanish? What's the best phrase you can learn? And I'm sorry, I don't know many other languages. So. Okay. Okay, ¿cómo se dice esto? How do you say this, right? And suddenly, with those 3 words, right, you've opened yourself up to an entire world of a language, right? You know, ¿cómo se dice? Oh, libro. Like, okay. ¿Cómo se dice? Bolígrafo. Like, oh, wonderful, fantastic. So suddenly, you have this prompting for the outside world just by you learning 3 words, and you could kind of learn the entire language, right? And that's an important thing, right? Like once you've got some basic elements, some just kind of building blocks of words and vocabulary, you can immediately then kind of consider this lofty layer of what happens when you put this word in. So let's go kind of A, B, C. So what happens if we have just A together, you know, B by itself, or we could have AB, or we could have, you know, AC, and then BC, right? We already have this like idea of once you've got some things, you can take the power set of them and get, oh, sorry, forgetting something crucial. And you suddenly have a whole layer of complexity just by considering the meta level beyond your first layer here. So you learn a handful of Spanish words, right? And then just by considering their kind of combinations and permutations and ability to prompt the outside world, you can suddenly feed into a whole another layer of abstraction, another step up. It's the same thing with here, right? So say you've got one transistor, right? Okay, good for you, right? But suppose you have like 100 of them, right? You can start doing stuff suddenly, right? And you can start doing stuff and have things which emerge which are greater than just the individual parts, right? I mentioned briefly this idea of ant societies, right? Of ant societies exhibiting these kind of emergent properties which are greater than any single one ant, right? And this is an important idea, especially when you even think about humans, right? Like humans always do this. One person has an idea, and another person has another idea, and then you can kind of consider, well, what's the interface of these two ideas? And you've got another idea, right? Like you can suddenly build things out of these simple pieces. And I suppose the merit of studying this is not only do you understand when can you forget about the details, abstraction, but what can you do given the pieces that you have, right? So I think this is kind of a an important piece. Tied into this, though, is this idea of levels of description, right? How do you describe something based on what level of even ourselves, right? I'm sure many of you ran across the part in Chapter 10 where Hofstadter talks about the paranoid in the operating system, and he talks about this program Perry, and he talks about the situation, and he kind of plays out, and I'll go ahead and elaborate stuff that wasn't in the book, but I think it's an interesting thought experiment. So how many of you would identify your bodies as part of yourself? Sandra, Naveen, Durs, Latif, Felix, Rishi. Okay. So wait, you guys didn't raise your hand, right? So you don't identify your bodies with yourself. Okay, so Latif changes his mind. All right. Okay, so for those of you who did.
Oh, is the brain part of my body?
Is the brain part of your body? Yeah.
Okay, then yeah.
Okay, so the brain's part of your body. Anyone want to change the votes? Okay, fine. So if I were to ask you, how's your leg feeling today? How many people would think that's a normal question? Okay, so we got plenty of normal questions.
How's my leg feeling?
All right. So suppose I then asked the question which Hofstadter asked, is like, so why are you making so few red blood cells today? All right. Is that a normal question? Yeah, go ahead, Sandra. You think it's a normal question? Do you have control over how many red blood cells?
No.
But they're part of yourself. It's part of you, right?
Yeah.
So why can't I address your red blood cell count as part of you?
Well, it's inside of you.
It's inside of you, right? But
You already said that your body is part of you, so.
okay, so you're accepting that as part of the logical consequence of the things you've said. All right, so good for you, because you're being consistent. Does anyone else suddenly feel like I've said something awkward? All right.
Maybe we shouldn't even say how does your leg feel today.
Maybe we shouldn't even say how does your leg. So
Yeah,
can we
because
never
who's
address?
deciding which is which?
All right. So suppose I don't know, Curran comes in and he's just got 2 black eyes, right? And I'm like, Curran, you look terrible. And he's like, that's just not an acceptable question, right? Because I'm referring to his physical appearance, right? So
Curran's mind is reflecting his physical feelings, his physical things, so he's like almost internalizing that picture and saying, oh yeah, that's me.
okay, so you're saying Curran's kind of self-model is inherently dependent on his body and his interaction with his environment, right? So then when I say, you look terrible, he views his own internal model and looks at himself as being terrible, right? So then that does make sense, right? But then what about the red blood cell question, right?
The red blood cells, I mean, usually you do not have like an internal model of your own red blood cells.
Okay, so yeah, right. You don't normally have an internal model of your red blood cells, right? But suppose you did, right? And suppose that and this is kind of going to be one of the take-home interesting consequences of this thought experiment, is what if you had internal access to everything that was going on, right? Okay, so everyone's going, oh God, it would be terrible. I mean, why would it be terrible? Like, I'd be like trying to walk across this room. And so I'd have,
some choices you make are not necessarily the right or appropriate ones.
yeah, so somebody should,
Say,
okay.
they'll stop me from
Wait a minute.
blood cells.
It's first you have to identify what's making the decisions. Perhaps the conscious thing doesn't make the decisions, but the decisions it is aware that are being made, it ascribes to itself.
Okay, repeat that last line one more time.
The decisions that it's aware are being made, it ascribes as being made by itself.
Okay, so you make certain decisions and you think that you're making those decisions.
I always ask, who's making the decisions, my neurons or myself?
All right. And I really wish I could have passed out the dialogue, like who pushes who around the cranium. Yes, and of Hofstadter's other dialogues. And you're right. And I wanted to kind of read this dialogue, but I don't know if we'll have time for it today. But the prelude and ant fugue gets this idea of symbols, right? Of these kind of larger emergent groups of neurons and little internal representations you have of the outside world. And to a certain extent, they make up who we are. Our internal models are the ones that then collectively make decisions. But on the other hand, we then have times where the emergent thing then manipulates our internal models of the world, right? So suppose like you're sitting in this class one day and then I'm like telling you, well, the universe actually isn't kind of deterministic. It's actually got this probabilistic framework, the quantum mechanics. So then you go, wow. And then you change your like base little mental model of the world, right? So there's this kind of weird interaction with hierarchies, right? So this is an interesting point, right? Because here there's very little interplay going down this way. But you know what? It does happen, right? Like, I think one of the best examples is your cell phone, right? Because you have this SIM card, right, as part of your cell phone, which actually, yeah, exactly. You take it out and it might not be operational, right? But you could also try putting it into another cell phone, and it might not work, right? And that's in part ascribed to this higher service, which is getting beamed back down. So there is a weird interplay of levels of software and hardware going on here.
Suppose we can have like a brain, you have your, perhaps your lower level neurons and neurons that talk about those and neurons that talk about those. So you're not having like this crazy software view, maybe the consciousness that's not even in the physical world is actually like attracting, like, or maybe like making changes to the physical world. It's like the physical world is making changes to the physical world, but those higher level neurons are sort of the ones representing the abstractions. The abstractions don't really exist, but it's like these neurons are like taking something from like the lower level neurons and they're seeing like the essential processes of them and then they're controlling them back. So you are like mostly your higher level neurons.
All right, so maybe you are mostly your higher level neurons, but I think an interesting example, and we're getting into details of the brain, which I'm not sure how it really works, but for example, with the ant societies, right, no ant is higher than another ant, right? All ants are pretty much created equal. Yeah, say again. Except for the queen. But still, there was this myth, right? There was this myth that the queen ant was like sitting there with her hyper brain, right, and just going, all right, tell forces A through B to go to sector G and attack and then bring over the leaves here, right? No, the queen ant doesn't do that, right? It's just like all the other ants, and that has probably 3 neurons, right, and can't do much with them. But it's the interaction of these very simple things which can produce complex behavior. Yes, Latif.
I just realized something. The thing is, you're not even aware of your own thinking, and the thing was like we often think that we're like very self-reflective, even though we're not.
All right. Yes, we are. We are. We do.
And
think
even reason is beyond us. Think how many times have you ever reasoned ever since you were a child? Most of the time you felt. You speak. You don't even know where the words are coming from. You don't know where your concepts are coming from. So how can we say we are highly self-reflective if we don't like even like most of the time reflect towards our own thoughts, our own feelings, and whatever, you know.
Mm-hmm. No, I mean, right, exactly. Like we tend to just kind of assimilate data about our outside world, and especially kind of the mental models passed on to us from our parents, right? That immediately start telling us and kind of training us, imprinting us, really like geese, from our first day to do certain things, right? And we can rarely break out of those kind of loops, out of those systems, right? But that's an interesting idea, right? It's this idea that what happens when we can't really scrape away at the boxes anymore, right? Like we try to, I mean, really what happens, I mean, why is psychology so difficult? Why is solving consciousness so hard, right? Because we're kind of like trying to like take out an eyeball and like peer back out at us and we're like, all right, what am I? Like, and that, I remember having this discussion with one of you after class, and it's this idea that, so evolution really kind of designed us to do certain things, and I suppose one reason why humans kind of took off with these abnormally large forebrains was because it was a good method for survival, right? We suddenly started getting together in little groups and planting things in the ground, and suddenly we had a really stable source of food. Or we would trick mammoths and run them off into cliffs and like have them fall on spikes that we designed and sharpened ourselves. And suddenly like problem solving was a really, really important thing for evolution by natural selection, right? So people who had kind of had these problem solving capabilities were selected favorably. But it's really nice to be able to run mammoths off cliffs and plant things in dirt. But what about the guy who is like, kind of at the bottom of the pack, kind of thinking, what am I? And then, the cheetah like attacks, right? As he's like caught in these thought loops about what am I?
Because he's always like crazy philosopher.
Right. So I mean, the philosopher was.
I mean, it's like you first get like problem solving, average, maybe perhaps go above average a little bit, and then you get like these monsters like so creepy. Those geniuses, they come along, they're like all the time they're like all the way over there.
Right.
We jump way too fast. We don't have like this infrastructure to like sort of like keep yourself from all these like enemies. You gotta slow down a little bit.
I mean, I think that's exactly like you do have these kind of figures which just seem, I mean, like Archimedes, for example. Like you want to talk about a guy who, I mean, the way one of my lecturers at Cambridge used to put him, Dr. Piers Bursell Hall, is he would describe these people as 9-dimensional hyper-intelligent beings, and like their bodies were just, their 4-dimensional protrusion into our worlds, and like that's because they were just, they were like practically aliens, which were in terms of their intelligence, and we just had no idea what they were doing, and that's almost dangerous, right? Like, I mean, we tend not to like or really go favorably with people who seem really out there, right? Like, and we kind of have a sad history of persecution, right? Like, and humans aren't always very nice to the above average. So, I mean, I was bringing up this idea of having intelligence and having these problem-solving capabilities, but that this ability to look back at ourselves and kind of be reflective as not being very good for evolution. And I've actually heard it suggested that our brains are actually evolved not to really solve the problem of consciousness because we're spending too much time, well, because it wasn't favorable in terms of evolution to actually be able to consider deeply and understand what's going on internally, having an internal model of all your thoughts. Like, we don't have a transcript of why did I make that decision? And like, well, in sector A, this happened, and this neuron fired, and this one, and that, is this, right? We don't have access to that. And that's in part because evolution kind of said, we don't want to give you access to that. We're going to put this together in a nice little rat brain. You're not going to have access to those thoughts, right? You're just going to have their consequences. So, I mean, it's a troubling idea. Sandra, you're going to say something.
Are there like any advancements with human involvement, besides like logical thinking? Is there a way to advance that?
Is there any way to advance logical thinking, to essentially advance humans?
Human advancements in thinking. Maybe there's another way that's better.
Okay.
I mean, if we did evolve from
Right.
simple as like bearing food.
Right. So I mean, to an extent, we are right now. like in this classroom. And the fact that most of us, including myself, we have bad vision. Like if I were really stuck out in the field, like I wouldn't have a chance to like sit and like look over books, right? I'd be futilely hunting and like not succeeding and dying, right? But our society has reached a level of technology and healthcare where people can go on and we don't have to worry about base survival needs. We've kind of, and I don't know how many of you have ever heard of this, but Maslow's hierarchy of needs. Anyone heard of Maslow? Well, have any of you guys done debate in high school? Do you even have debate teams or classes? They don't have these programs here? Gasp! All right. So Maslow said we have this kind of hierarchy of needs before we can do anything. And kind of at the top here, he had kind of essentially transcendence, right? I'm actually blanking on the exact word which he used. This is embarrassing. But either way, I want you to Google this. Abraham Maslow. We have hierarchy of needs. I can't spell either. Is there an A here? No? Okay, it's just A. It's just R. H-I-E-R. Hierarchy of needs. Thank you. And we have this self-actualization. Haha, haha. There you go. And we have kind of like food, water, shelter. And this is really what humanity spent, most of our early development just staying at this level. Fantastic. And, he roughly describes this as physiological needs. And then we have safety, right? So we have, security of body. I'm just going to go ahead and write safety in here. Pull that out there. Safety. Love, belonging. Esteem. You have to at least think somewhat positively of yourself. And then we get to self-actualization, which Wikipedia describes as morality, creativity, spontaneity, problem-solving, lack of prejudice, acceptance of facts. And really the argument, and a lot of people use this kind of in a scary, slippery slope, say, well, look, we're going to protect you by constant 24-hour surveillance because before you guys can even think of doing anything up here, like you just need to be safe in your homes, right? You need to be safe from terrorists. So before you can even do any of this, right, you've got to have this, which is funny because we tend to do things which would infringe on inherent properties of self-actualization, like freedom of speech, freedom of thought, et cetera, right? But you can in some ways say that humans have been trying to climb up this ladder, and that even us as individuals in our lives kind of, our parents provide us with food and shelter and security and safety. And good parents should give us a feeling of love and belonging. And this then enables us to do things like, go to college and, think about Immanuel Kant and other philosophers and stuff. Yes, Latif?
Couldn't being under 24 hours surveillance sort of take away our feeling of safety? Right.
So, and the argument goes both ways. You could also not feel safe by being surveyed. But, this is a debate for policymakers, not necessarily for me right now. But you're right. Sandra, I'm glad you brought up this point of this idea of humans trying to advance. And then it's kind of sad to say, but most of us here in this classroom are really occupied with we're all kind of up here in this triangle, right? And we're worried well, what about logic? Well, is computer science going to lead us to it? And we're worried about this very tippy peak, which is enlightenment, right? Whereas there are plenty of people out in the streets today who are worrying about these things, right? They're not worried about, like, is Gödel's incompleteness theorem going to give me my final understanding of consciousness in the brain, right? I mean, just think about how far of a level that is, and even think of how far of a level we've historically come as people, and kind of escaping the kind of brutish and harsh natural selection on this level. And we've kind of now been engaging in a selection on this level. And as you guys watch in Waking Life, next lecture, you'll actually get a really pumped up philosopher who will talk on this film about this idea of kind of neo-evolution and the neo-human. What happens when evolution starts no longer acting in terms of genes and security and safety here, because we as humans, we don't usually worry about this anymore. Like now, evolution is happening on a cultural level, on a mimetic level, for those of you who know what memes are. But we're going tangential right now, and I want to pass things over to Curran, who's got lots of goodies for you once again, and go through this idea of climbing up pyramids and this interplay of levels and descriptions. So as such, you guys get your 5-minute break while we reorganize things, and see you all back here. So what are some consequences if those things aren't balanced, right? So what happens if you suddenly don't feel safe, right? Okay. Well, I think some clear consequences based at least on this model is the idea that if we don't feel safe, right, we're not going to want to pursue anything higher, right? Like, we're definitely not going to feel loved if we don't feel safe, right? And we're not going to have any kind of self-esteem if we don't feel loved, right?
How about Gödel? I don't think he felt safe when he was doing that.
Okay, so you're right. There are these few kind of crazy characters in history which have been ultra paranoid, not felt loved, and just been essentially like schizophrenic, right? I mean, look at Isaac Newton. You want to talk about a not nice man. He was a very, very evil man. In fact, as his, I think, 32 years as head of the mint, where he's responsible for giving people their lives back, because in those days, clipping coins was punishable by hanging, right? And he would never clear anyone's sentence. I mean, everybody who went up for coin clipping got hung underneath Newton's. So back in the day, right, coins were actually silver, right, because the metal itself had inherent value. So what people used to do is they would clip little chips of silver from it every time they came into possession of a coin, and they'd have a pile of silver, and you could turn it to like another coin, right? So you just kind of had another coin spring from nothing. Of course, like you can imagine, like you would have to write letters to the warden of the mint, saying things like, "Oh, I'm so sorry, Mr. Newton, sir. Like, I clipped only 2 coins, and it was so I could buy an extra loaf of bread for my family. Mrs. has another bun in the oven. Like, I've got 3 kids I need to feed, and this guy's probably illiterate too, and like, struggling with writing this letter, right? And Newton's like, huh, like, hang him. So he wasn't a very nice person, but he was brilliant, right? And he kind of went higher up this pyramid than any of us can really hope to. So yeah, there are some defects in this model.
But on the self-actualization, didn't you actually say morality was one of them?
Yeah.
So you can sort of get rid of it.
All right. Don't need morality. But I mean, ideally, we'd have this kind of. Now you have to also remember, Maslow was kind of a philosopher of the 60s and 70s and believed that enlightened people would be loving and happy and all the time. You want this turn?
But can you actually say Newton was enlightened?
No, I don't think he can, right? But I mean, he was. If you want to talk about the qualities of intelligence and problem solving, I mean, even when he was old and people were trying to solve the problem of the brachistochrone, the shortest, what shape slide would enable when you drop a ball down it to go from point A to point B in the least amount of time. Like, this was being circulated through European and British mathematical journals for years, right? Nobody really came up with a good solution. So somebody finally passed it off to Newton, you know, comes in at like 65, right? And you just kind of go, oh, don't insult me with these easy problems. Stood up that night and solved it in, you know, a couple hours. Like, I mean, that's just the kind of guy that he was.
So would you say that he didn't let anyone off?
I don't think so. I don't think he ever let anyone off for 32 years of being one of the men.
Yeah.
I think that could be right. So, Curran, do you want to talk about this?
You can start talking about it.
Okay. Okay. All right, so this is actually this gives you an idea of how Curran and I plan for lectures. Actually, this is the only time we've ever used a whiteboard. So we have this idea of I wrote this question on the board for Curran. I said, if he had to administer a test to decide whether or not, it kind of runs off the edge, someone was destined to be a computer scientist, what would it be?
Oh, I said computer.
You had to be a computer. Yeah, I guess it got clipped somehow. But either way, like, you know, just by forcing you guys to vote by those boxes, I went ahead and I had this. I was trying to get at what levels are you guys most interested in, and you know, I talked about, like, if you're a physicist, right, and you're sitting in kind of high school biology, right, someone might tell you about organs and things like this, and if you were a physicist, you would be like, okay, great, whatever, tell me more, and they'd be like, okay, well, these organisms are made out of tissues and cells, and physicists would say, fine, yeah, what else? Well, those are made out of, like, you know, these big proteins and these kind of organic molecules. Physicists would be like, okay. And those are made of, you know, chemicals, which are then made of atoms, and then they'd be like, oh, now you're starting to make me interested. And so then a physicist really occupies themselves with pushing downwards on this level as far as possible, right? Particles, forces, quarks, strings. So you can almost characterize it as a process of reductionism. And this is even true when you're thinking about large things like supernova, galaxies. You're trying to reduce these large-scale phenomenon in terms of explaining them in fundamental forces, F equals ma, things like this. But then, like, what about, you know, I forget what's the statistic, but I want to say something like 50% plus of all people who, for undergraduate majors, do like humanities, things like law, history, creative writing, things like this. I mean, if you're one of these people, like, you don't ever even look below this line, right? Like, you're really caring about, like, kind of what happens here, right? What happens when you take your basic building blocks of say, fear, hunger, desire, and selfishness, and you take linear combinations of them, and you're like, well, I want to give, like, 75% fear with a little bit of desire, and that's going to be a new emotion called apprehension, right? And then as you kind of build up here, you start going with levels of description starting on the levels of emotions and then building up to things, especially if you're like kind of a literature major interested in what your language can do. So then, you know, we keep asking, so like, what's an engineer, right? I mean, who here thinks they like engineering? Okay, great. So like, you guys see, or you might see, just, you know, everyday materials. Like, well, you know, you're kind of like your own little MacGyvers. Like, give me a toothpick, a rubber band, and, you know, a piece of dough, and I can, you know, pick somebody's lock, right? Like, I mean, like, that's just what MacGyver does. And you're always kind of, or, you know, I hate to generalize, but you're interested in how you can take kind of base, ready, efficient materials around you and then create practical, effective solutions. And you're always kind of working in this domain here, maybe even going from small projects to citywide ones. So then, still, like, we ask, so what makes a computer scientist? And I say that really fundamentally, a computer scientist is a lot like a mathematician who doesn't really explore the physical world and its layers of abstraction, but instead live in kind of a Platonic world. And their atoms are kind of sequences and series and logics and grammars and calculus and algebra and geometry. And you just get to play around with these things. But I would say that inherently, kind of what makes a mathematician and computer scientist is looking at just patterns and kind of abstracting away any details. I was really sad when I stopped really being interested in biology, because I used to love biology. I'm like, oh, isn't this great? Look what evolution produces. But really, once I learned about the theory of evolution, I realized, well, that pretty much explains it, right? You have a couple roll the die. You have, genetic mutation, phenotypes, selection, repeat, right? And once the theory was there in front of me, I said, well, I'm glad, Darwin solved that problem. I don't have to worry about it. And suddenly biology became less interesting to me, just because, and what I guess ultimately boils. Say again, Sandra?
It's not mystery, so you're not curious.
Right. I mean, like, the theory was there. And that kind of, like, I guess puts me as kind of theorist and philosopher, is that I don't care about the details. Like, and, people spend their entire lives, like, studying the action of this protein on thing X and Y, right? But I don't really care about the details, right? Just the conceptual process. But I don't want to, bias any of you guys. I mean, everybody has their own kind of take at things. And, even Curran and I had kind of differing opinions about what was interesting and what you guys find interesting. So I'm going to turn things over to him.
So something that was really cool that we noticed about these is the universality of like things that being on lower levels and things emerging out of those lower levels into higher levels of things. Like electrical engineering, like you said, transistors and stuff. You have all these different layers of things that can happen up to software, and with neurons in the brain and thoughts, and with biology, like DNA and RNA and replication and whatnot, reproduction, and then that leads to evolution, which is an emergent property. So I'm going to show you some programs that I wrote that exhibit some emergent properties. So this is sort of a physics simulation, but it's discrete. It's not continuous. And physics is modeled, as continuous, integrals and stuff like that. So here I'm sort of doing integration, but it's discrete. So you have this sort of weird error, that makes it not exactly like physics, but it's still really cool. So the blue and the red things have different charges, and there are Coulombic forces acting between them. So I'll just play with it. Coulombic forces is like plus and minus, opposites attract, and when they're the same, they repel each other. And so we can change, all these properties. And the color reflects how charged they are. So this thing that's really weird. Like this would never happen in real physics. Like, where's this strange energy coming from? And I think it's because it's discrete. It's discretized and not continuous. But it's still pretty cool, pretty interesting. Yeah, repulsion. And now it's stable. So what I want you to keep in mind in looking at all these is that with every one of these examples, it's very simple rules, or pretty simple rules that govern the behavior of each individual one. And the rules that govern one of these particles, one of these balls, is no different than the rules that govern all the other ones. So these simple rules that are local lead to global phenomena, emergent behavior. This is what emergence is all about. Things at higher levels emerging from simpler things on lower levels. So for example, like crystallization in nature is an example of an emergent property. So here's a set of presets, a set of settings that leads to crystallization. It's like tuned to crystallize.
And see, that's an interesting thing to point out, is that we have this level of description, which you just described. We call this a crystal, right? We don't say it's the arrangement when particle I acts on particle J and has the following charge, right? Like that level of description is too fundamental. But this higher level description of a crystal is much more convenient, right?
Yeah. Yeah,
Even
Latif.
if we do say crystal, we mean exactly the same thing. It's like we're just dodging around exactly what the thing is.
So you said that when we say crystal, we're not really saying the thing. We're saying, we're sort of, beating around the bush, right? Saying,
Yeah, it's like, okay, so we have these crystals. They're like compositions of different particles that usually attract each other to like make certain easily discernible shapes. That's
Sure.
the definition of crystal. But once you like see it as it is, it's like the set of all these different configurations of matter such that this properly holds. You just like.
Yeah, I mean,
just giving it a name for
that's
something.
exactly. You're exactly right. So we say crystal, we mean a very sort of high level thing. And this is what I mean when I say low level and high level. Low level means like describing the exact way that the particles interact and different things that they do. But crystal is a higher level. And so the lower level details could be different. Crystals form in out of all kinds of different substances in nature. And this, we can call it a crystal because it sort of resembles the crystals in nature, that it has this regular structure. But yeah, you're right. It's sort of glossing over all the details. It's existing at a higher level. It's a higher level of description.
So it's like there's this mathematical theory of category theory. So you can say, okay, we have like these different fields and everything, but what happens over here can be mapped to exactly what happens over there. So like when you're like describing things as crystals or whatever, you just like almost speaking like category theory language, like it's just like normal speech.
Justin knows more about category theory than I have no idea about category theory.
Yeah. Oh, I mean, one wants to just tell you to be careful, but two, yes, you're kind of right. Like you're just looking for general features and kind of systems, and then kind of ascribing to that universality, right? Exactly. And I wanted to point out real quickly that what I wrote up there on the board, Fij equals K Qi Qj over R squared. I mean, that's just your rule of attraction for Coulomb, right? Like, should be a minus, right? And this is how, and we have this kind of level of description for the interaction between two particles. But what happens when we have, in particles, right? Suddenly the equations become really hard to solve, but we start getting really interesting geometric behavior, which is easier to describe up top, right? But we're going to kind of hit your idea later, because we're going to see examples where we see the similar concept of force, but there's no forces going on, right? We'll talk about that in traffic flow and things like that. We don't actually have cars ramming into each other, but we still get the same behavior. But we'll save that.
So this is another set of parameters that leads to this droplet sort of forming, which is pretty cool. And here's the n-body problem being simulated. Oh, there it is. So it's just things orbiting around each other based on pretty much that equation that he wrote on the board.
Yeah, except you replace the charges with masses, because Q, I, and Qj represent charges, and instead you have masses.
Something like that. Yeah. But that's it. It's
So
just
that's one that's unpredictable, right?
yeah. This is
Actually, it is predictable, but you have to run the program.
It's deterministic, not predictable.
it's deterministic and not predictable. It's chaotic because it becomes nonlinear. Is that correct?
So the only way to know what's going to happen is to run it.
Yeah, and even then you're approximating. It's not continuous, so you're going to get an approximation of what might happen. So yeah, you can't really solve the n-body problem.
So what if you got your mind, right?
Hmm?
So what if it is like a different bunch of programs, like even in that thing you only talking about particles, those are like simple stuff. But when you have minds, you have like a bunch of these stuffs going on together.
When you have what?
When you have minds.
Minds?
Yeah.
Yeah. So when you consider a mind to be one of these particles, right, in society, interacting with all the other minds around it, right? This is called agent-based modeling. This is agent-based modeling. Flocking is when you have...
But the problem is for the particles, you have definite rules. But for societies, even the minds themselves are hard to predict.
Yeah, exactly. So you're saying, you know, if we model society as this agent-based model where each agent consists of a mind, it's even, you know, more impossible to predict because the mind itself is not really predictable. The mind itself is emergent out of the things that comprise it. So yeah, I mean, that's
an interesting idea of going backwards, right? Starting with behavior and then trying to figure out what rule governs it, right? So it's kind of like, how did Newton figure out this law of attraction, right? You start from a behavior and try to deduce or infer, better yet, what the law between two things is. And what we're going to see today with both cars and I guess even with people is we don't know the people. We don't know the interaction between two people, but we see the overall behavior.
So here's another version of that program where you can get these molecules to form, which is really fascinating. These like stringy molecules. So it's another kind of emergent behavior. See, there they go. It's totally a molecule. Check it out. And the rules are pretty much the same. I don't know exactly what particular rules they are. And here it is in 3D also. So if we wait for a minute, these molecules are going to form in 3D. So I mean, yeah, emergence is really a cool concept. So here's this molecule in 3D.
Could it be that the world is constantly describing itself in like different levels of description?
Could it be that the world is describing itself in different levels of description?
Yeah, because you do have that, and then you also have like something higher, like a geometrical shape on it. Yeah, something like that. But you can also like describe it as a bunch of different particles being attracted by different forces. You can also like describe it as like somebody actually looking at that thing itself.
Yeah, who's doing the describing?
Yeah.
Yeah, I mean, it's what Douglas Hofstadter calls a tangled hierarchy, right? Where it's not really a hierarchy because things on lower levels are related to things on higher levels and can have influence back and forth. So just like you said, you know, the world is constantly describing itself, interacting with itself, you know, between different layers, different levels. And it's just like...
Can we say that the higher level also like influences the lower level, or can it always just like lower to upper?
So you said, can we say that the higher level influences the lower level, or does it always go upwards? Well, no, it definitely does not go only upward, because think of software, right? If I run this program, this next program, which we'll just watch for a while, this program itself is controlling the transistors and whatnot that's operating.
But it's not really controlling the transistors.
It's not really controlling it?
No. Look. You got the code, you put it into the RAM. There's something like it's like represented by like different electrical activities, and those electrical activities are like computed, and they're like different like hardware is attached to those, and those like different codes like match like different hardware behavior, and then you have the little software program running. Yeah. There's no higher thing controlling the lower, it's like the lower one. It's always the
Yeah, it's all one. It's all one thing. It's just we think about it in terms of high level and low level. So you're right. I mean, the hardware is controlling itself, right? But it's based on what we put into it and what we tell it to do it at a higher level. So I mean, the software that I wrote, which came from my mind, which was, if it's at a higher level, in a sense, than the hardware, like this projector that's actually projecting pixels. I mean, so that's what I mean when I say the higher level things influence, you know, affect, control even, in this case, the lower level things. Yeah, it goes both ways. And like if a transistor were to crap out right now, it would control the higher level things because it would just stop working.
It's concept of causality, I guess.
Causality goes.
That doesn't make any sense. Okay, how can a software program control hardware?
So this software program is running on the hardware, and it's controlling this projector, right? It's controlling the hardware,
Okay,
physical
is it telling you
things.
what to do, or is the hardware telling itself what to do?
The hardware is telling itself what to do, but only after I've told it what to do.
Right, but even if we were to remove Curran, right, and we just had the software executing by itself, you're right in the sense that it's always just the hardware. It's just the hardware, right? Software doesn't really like exist, right, in this ethereal realm, right? It's software is still just what's going on the level of transistors and stuff. It's just that we as humans use these levels of description, and we talk about the software as its own entity, even though it's fundamentally still just caused by the interactions of electrons and transistors and such.
So here's another example, which is traffic flow. So traffic flow is a perfect example of emergence and what it means. So like these little bars, it's just like one lane of traffic that's just going, and it repeats itself. But so each one of these cards is like an agent, right? It's a lower level of description than the waves that we'll see right here. So say there's a red light, right? So the traffic gets backed up a little bit, and then the light turns green again, and then they go. And so you see this thing on a higher level. It's this wave which is propagating back. So we say the wave, is a thing, and we can describe it as an entity, but it's at a higher level than the cars themselves. Even though it's comprised of the cars, it affects the cars, and the cars affect it. That's the same thing with software and hardware. You still don't get it?
I guess it's really just an issue of reductionism versus holism. Right?
Yeah, which is exactly
Do you
what.
feel like everything can be understood as reductionist thinking? Or sometimes we have
Well,
to...
at times you just have to think, okay, how does me, for instance, how do I come from interactions of particles? You have to do synthesis in that. Right.
But does that explain you, right? And Hofstadter asks another question in the same chapter is, so the guy who runs the 100 meters in 9.3 seconds, right? Where is the 9.3 stored? It's not, right?
It's encoded in his brain, and what he calls those brain signals is 9.3. That's what it says.
Right, no, but 9.3, the fact that he ran the 100 meters in 9.3 seconds was the result of, training, him getting good traction at the start. I mean, it was really an emergent thing, right? It's an epiphenomenon, as Hofstadter calls it.
So here's a good question to ask yourself regarding things that are emergent. Do you exist? Because what are you? You ever ask yourself, what am I? It's an area where it's easily confusing because, you're an emergent property from the things that you're made of.
The problem is, it's not to say, do I exist? I mean, the answer to that question is almost the same answer to the question, what am I? If I describe myself as there's almost two different parts of myself. Now, myself as described by brain processes, maybe some part of my brain has a description of what I've always done, and also my beliefs about myself. And also another part of the brain has almost a way of me going back and also maybe having this self-conscious awareness of seeing the world, living my description of myself.
Yeah.
So which one am I? Well, probably I am the thing that the brain describes I am the self. I am not the thing that's aware of the self. Because the thing that's aware of the self only exists to be aware of that self. So I cannot be the awareness, I must be the one that's being aware. If that makes any sense.
So you're basically dividing yourself into the observer and the observed, right? The thing that...
I'm not the observer, I'm the one that's being observed.
So you're the one that's being observed. So what is it that's observing then? It's not
I
you.
know what it is like this like added structure of like self-awareness.
So that's a you know, these are the issues that Buddhism grapples with. And it well, I don't know. I'm not, you know, enlightened. I don't know the answers. So I'm still as confused as you are.
Like, I think one of the main problems is that like you think too much. You know? If humans just stop thinking, everything will just be fine.
So Latif just said, if humans just stop thinking, everything will be fine. And that's what the Zen masters say also.
Well, it's also saying we should just, you know, be trees, right? Which also just says, like, let's give everybody, you know, mandatory frontal lobotomies, right? So no one can, like, think any abstract thoughts or get worried about anything. I mean, we'll just be reduced to basic hunting, surviving if we can.
Yeah, it's like what Gödel says. Once you like start talking to yourself, you're speaking nonsense, basically.
Once you start talking to yourself or about
talking about yourself, you know. It's like okay. Here's me. If that makes any sense, because who's speaking? Talking about myself.
Yes.
My self-reflective process that I'm talking about myself, like some of the most abstract processes of my mind, that means they don't know the details, therefore they should not really be talking about myself.
So you're essentially arguing that self-reference isn't like a well-formed thought.
No, I'm not.
No?
Yeah.
Okay.
Yeah, I mean, that's true. Like when you talk about yourself, the thing that's talking is not well informed about what it's actually talking about, right? So.
It goes back to the complexity of the brain, because the brain is so complex that it can't even talk about itself without talking about nonsense. You know, it's just like almost like looking around like on a weird fractal, on a weird pattern. It's like, oh, this may be, this may be, this may be. It's like talking nonsense. It's like going just randomly.
Yeah. So essentially, you're saying talking about yourself is just sort of rambling nonsense. That's like
it's sort of like intuition, like our mathematical intuition.
Yeah.
You see like some structure here, some structure there. You say, oh yeah, that may like reflect some mathematical laws or something. But it's just a hypothesis. It's not really. It doesn't have to be true.
Yeah. I mean, so you're getting at some really deep questions that we all have to face if we choose to face them. So I mean, I encourage you to keep.
Or as Sandra says, stop thinking about them.
Yeah, I mean, that's totally it. Because if we keep thinking about these things, either we'll get stuck and go insane and not be able to function, or we'll become enlightened, maybe. I mean, I don't know what that is even.
Well, no, I mean, be bold, right? But not too bold, right?
And this gets back to what Justin was saying about earlier, like, you know, introspecting and asking these questions, it's not favorable to our survival. You know? So, in a sense, we've been programmed to just ignore them, you know, and just live our lives.
But we're hoping to evolve past that.
But yeah, we're hoping to transcend that. You know, and
Perhaps when we build a conscious machine or something like that, we shouldn't like give it the ability to analyze itself.
Yeah.
Maybe like the worst thing any person can ever do is to actually know how they think, who they actually really are. I think H.P. Lovecraft once said something about that. You know, it's like the best thing that we I think ever have is that we in any given time we don't ever have like a complete model of the world, because if we ever did, it would be so frightening.
Yeah. I mean, but exactly. On the other hand, though, we're inherently curious, right? And we inherently want to understand bits of things. And I don't know if we can ever have a complete model of the world as it is. But we can sure as heck try, right? And you know, the bottom line is you should just do whatever makes you feel good. If understanding part of the brain does that, go for it, right?
But you can never fully understand the brain.
Don't let that stop you from trying.
Look, it's like one of those existentialists, you know. You got like a man like holding a stone up a mountain or something. Once they get there, the stone is dropped and they go back again. You know, the goal is pointless, yet they're like doing the process.
So I mean, you're essentially arguing that understanding the brain is a pointless goal.
You know, why do something that you never achieve?
Yeah.
So even if you achieve it, what's the next step?
Oh, you'll make yourself better.
Okay, so yeah. I don't know.
So,
I'm
yeah.
going with Sandra's idea.
What was Sandra's idea?
Like if you there's puzzles, right? If you finish the puzzle, you're done, right? So what else is next?
You make yourself smarter so you can be harder to like understand yourself.
Well,
Which
it's
is-
like essentially screwing the next generation over.
So what you're getting at, actually, you know, because what you're saying is sort of like this. Like once you understand a certain amount of yourself, you've added another part of yourself which you don't understand.
You mean the part that actually understands itself is the part that you actually don't understand.
Yeah. So once you come to terms with yourself, or so you think, that part of you which has just come to terms with itself, you don't understand. That is analogous to adding G to number theory, because it can be Gödelized again and be proved incomplete yet again. And then you can say, oh, well, it's not incomplete now, so I can just add that in. This is a big part of some chapter in Gödel, Escher, Bach. I forget which one. But it's essentially, you can never understand yourself. I mean, it's a dangerous use of Gödel's incompleteness theorem. It's probably not well, based. But it's, I don't know, something to think about.
But you can always do like the complexity thing, you know. I think there was some guy that he did some calculations, and he came out, you know, once a system becomes so complicated, it reaches a point that it can't understand itself.
It'd be interesting. If you could pull that reference, then it'd be good to see. But yeah, tell me if you can do
I think somebody already told me. I don't know who it is.
that. Okay.
Yeah, I mean, once a system gets to a certain point of complexity.
I mean, if somebody else can't understand it, how can it understand itself?
Yeah. I mean, we can't understand ourselves in the sense of everything that's going on because we can't introspect on our own neurons, right? You know, our neurons, in the case of agent-based models like we're talking about, like check this one out. This is pretty cool. The balls on top are being pulled upwards and the ones here are being pulled downwards. So there's a sort of stability. And I think there are the same number of balls. I'm not sure, but somehow I made it so they equal out. And this is just agent-based modeling, applying these force equations, but only between the balls that are connected to each other. So I mean, it's pretty close to physics, and it's pretty cool. So what was I going to say about agent? Can someone remind me what we were talking about?
So, I mean, I wanted to kind of comment about
Yeah,
this
go
idea
ahead.
of modeling the universe. If you're really interested, I would recommend a book called Programming the Universe by Seth Lloyd. And essentially, it says, well, the universe at the bottom uses quantum mechanics, right? And we can't model quantum mechanics effectively on a classical computer. In fact, we need a quantum computer. But the universe itself is a quantum computer, and the only thing which could model the universe is the universe itself, right? So we can't build, I mean, we'd have to build another universe to model the other one, but why do that when we already have the universe which is computing itself, right? So, I mean, it's a very interesting book, and Seth Lloyd's a very prominent physicist, and he's a mechanical engineer here at MIT who works with the Santa Fe Institute of Complexity Science. And it's a very good book, but I think it gets kind of at the heart of the problem, that really the tools that we need to describe the universe is really the bits of the universe itself, right?
But don't you have like some of those weird properties of infinites? You know, when like the thing, like the whole thing is infinite, right? But even in that thing itself, there's another thing that's also infinite. So you can have like a quantum mechanical computer inside a universe that's also
Right.
sort of like emulating the universe.
Yeah, but it can only emulate pretty much a part of the universe of equal size, right? A quantum computer, in involving 7 quantum bits can only essentially model something that big, right? But the information content of the universe really is equal to the amount of information the universe can compute with, right? So you need a computer as big as the universe in order to model the universe.
Down to every detail.
Down to every detail.
So all we can do is approximate on higher levels.
And do this chunky descriptions, abstract away details, try to pull out salient features.
So I remember what I was going to say before. So this is an agent-based model where each one of these is considered an agent. And this emergent behavior happens where this structure comes together and just moves around. So I remember I was going to say, if you think of your brain as an agent-based complex system, in a sense, which is really what it is. Neurons are just interacting with each other and outside stimulus. So roughly speaking, it could sort of be considered this agent-based system. And the neurons are analogous to the balls here. And the formations and the actions of what's going on at a higher level that are emergent is analogous to your thoughts. So when your thoughts try to introspect on, well, I don't know. I can't really go much further.
Sort of like a sea of thoughts. You can't get back. You can't get to like the other island.
So, I mean, you can't understand each of your neurons because you, I don't know, this structure can't, introspect on what it's made out of because then it wouldn't be itself anymore. I don't know. Yeah, quantum mechanics again. I don't know. So one more example, which is pretty cool, which exhibits sort of optimization. I can click and add balls, and they connect to each other. And each one of them has this, every pair has this sort of optimal distance away from one another. And it sort of evolves to this optimal distance. So nowhere in my program do I say, if you have three of these form a triangle. It's an emergent property due to these various local forces trying to achieve local optimal solutions. And this happens in chemistry a lot. Particles and molecules always try to find the lowest energy state. And that's how molecules exist. But it's not as simple. I mean, so here's another one. When you add 4, this is the optimal configuration. And it just evolves into it. And this is how physics works. And with 5, it makes this star shape. But this program is not as simple as I said it is. There are some strange rules that say when and when not to make edges between them. Edges are connections between the balls. So I can do something like this. I can just drag and make a ton of things. I think I don't remember the rules exactly, but I tried to make it so that it was only local, and things that are far apart don't interact with one another. They only go through intermediaries.
It's like in resonance, like it's forming and breaking bonds.
Yeah, so yeah, it's like resonance, sort of. Resonance. I don't remember exactly what resonance is, but it's
yeah. Well, it's resonance just when you're oscillating between kind of two superimposed, two possible states, right? And I mean, really, that's what's going on here, right? Is that you have these different possible stable arrangements, and there's kind of this equilibrium that is diffusing back and forth between.
Right. So there are these two stable arrangements that lead into one another, so it just oscillates between them. So I mean, it's sort of roughly molecules in the world and stuff. So if I can make it all the way around, I can make a cell. I've done this before, where you have this sort of membrane which forms, which is exactly like what happens in real biology.
Oh, yes.
There it is. Yeah, more or less. So in biology, you have these hydrophilic and hydrophobic ends of lipids, and the hydrophobic ones go on the inside, and they all pair up with one another. And the hydrophilic ones go on the outside. Hydrophilic can interact with water, and they're soluble with water. The hydrophobic ones, they're fear of water, so they try to go to one another. And so you get this sort of structure. I mean, it's not exactly analogous to this, but it's sort of close. And it just sort of assumes this optimal configuration in our cells. And you know, if it weren't for this sort of emergent, this fundamentally low level, you know, lower than the level of cells, this is membranes, you know, without this emergent property of lipids, we wouldn't exist. You know, it's a fundamental thing that holds us together all the time, our cells. So I mean, us as humans and all biology is just built up of these layers and layers of emergent properties. So I mean, layers, I mean like, so these are cells and, no, these are like lipids. And one level above that is these sort of stable spherical membranes. And then a level above that is the interaction of cells with one another to form organs. And then a level above that is the interactions of organs with one another and the bloodstream. And a level above that is, you know, the brain interacting with that, you know, in a positive way. So we just built up all these crazy layers everywhere. You know, everywhere in biology you'll find this sort of thing. So it's emergence. You know, it's really cool to grok, you know, emergence. So any thoughts, anybody? Questions? We're just about out of time.
What I see is that almost like every single little thing can like be put down to like the smallest like basic physical like processes. So the only problem I think we have is like to sort of develop a theory of organization, like sort of invariance of properties. Like to say, you know, even though like I have like almost like 1,000 of like my brain cells have been like destroyed in like maybe like the past day or something. I've been drinking or something. You know? I'm still me. You know? What about my brain organization still says, okay, this is still Latif, it's like it's still the same thing, you know?
Right. I mean, robustness of systems, right?
Yeah. Yeah, that's totally what you're hinting at. Robustness. Robustness means, you know, you can change parts of it, like so for example with a wireless mesh network or something. It's robust because if you knock out, you know, a bunch of nodes here and there, it still exists as a network. Yeah, and so what you're saying in your brain, like even if you get completely wasted, you still know that you're yourself. So it's robust to these changes.
You know, suppose okay, some brain cells are destroyed. Okay, other new ones are built, are like made up to like make sure like my self-concept is still preserved. But between those brain cells being destroyed and new ones being like created, where am I?
Well, okay, so you're saying, so say if some brain cells get destroyed and your concept of yourself is temporarily is dissolved and then new pathways or whatnot are formed that get your sense of self back.
So at some time I don't even exist anymore.
So this is I mean, hinting at a very important point that, you know, what are you if, you know, like you are an emergent property. Your sense of self is not the actual neurons. It's this thing which exists on a higher level.
Yeah, but
so
it has to be supported by the neurons.
Yeah,
there, you know,
you
have to create that structure.
Yep, it's a supporting structure. But yeah, you're saying so if you temporarily dissolve, then yeah, you just don't exist. I mean, I don't think there's anything more to it, and you just reappear. You just disappear, reappear, and things do that all the time.
Okay. That could be the case if I was data, you know. I could be knocked out and then I could be rebuilt and okay, I'll be the same me. But is that really me? Do I have to have continuity to be really there? I mean, even like you can't even have continuity because it has to take some time for the neurons like to all travel. So you know, even like the fact that you know I see a continuous world, maybe that's even an illusion. You know,
that's
signals have to travel.
Yeah. Right. So I mean, fundamentally, right? You have the cells in your body are replaced every 7 years, right? So you 7 years ago are not made of the same cells you're made of now, right? So there's just this idea that what constitutes you has to be stored at a higher level of description, right? That like you can take entire chunks out at a time and still have things okay. And what makes us different than a computer is that we can be running us, right, just like we would like to run a computer and be able to, I don't know, swap out a few transistors and maybe even like, you know, like a stick of memory, right, and still have everything running smoothly up top, right? Because that's what happens all the time with us, right?
But you can also kick out some memory. You're not going to be you.
Yeah, so then there does seem to be certain points of you which are really critical, right? That there are certain like key nodes that if you knock those out, like, and this is really kind of almost a problem in graph theory, and this is really something that we've used in kind of understanding terrace networks. Is like, sure, you can knock out a few lower guys, but you're not going to destroy the whole network. But if you knock out that guy, is it the whole thing going to come to the ground, right? It's just like if you like, you know, get a pole to the head or something, right? Like suddenly you could be, you know, done, right? Whereas if someone cracks you in the leg, right, you're going to be okay, right? So there, yeah, it's almost like a graph theory problem fundamentally.
So a lot of the things that we're talking about are problems of complex systems. And you hinted at before, you said like, well, so maybe what we should do is, you know, try to come up with a general understanding of the kinds of systems and, you know, theories about them. And this is complex systems. So this is what like New England Complex Systems Institute does, or Santa Fe Institute in California.
New Mexico.
Oh, New Mexico.
Yeah.
Well, yeah.
Sorry. But yeah, no, I mean, there's a lot of interesting stuff to go on, and whatever interests you, like, I hope we can plug that interest. And please talk with us after class, and we can, you know, kind of point you in the right direction. And we completely open. We hope that's open. Ah, you're attached to me.
I am.
No Coulombic forces here.
Yeah.
No. But yeah, so I mean, please feel free to come talk to us after class, and we can try to suit you up with your particular interests. And even if you don't know what you're interested in, or you have an idea of, well, that was really boring, but this was okay, we can maybe kind of cater to your interests. But you know, this was really kind of the last lecture, and I wanted to thank all of you guys for coming here, for bringing your questions, for bringing your open minds, and you know, I think we've had a really good semester so far, and I hope you guys enjoy waking life in the next lecture. But other than that, any last questions before I say goodbye and bon voyage? Latif.
Paradox that I've been struggling like for the whole day here. You know?
Okay.
So you have like 0 to 1, right? And you have 0 to 2, right? Both of them like have an infinite amount of elements, right? But it could be proven that like as many points from 0 to 1 as to 0 to 2.
Yeah.
So why is 2 still greater than 1 if there's as much stuff between both?
Because we don't use as a well-ordering operation the number of points between this and that, right? We just start off with kind of, here are the integers, here's a well-ordering on them, and that's how we go.
So you just put like this structure on, it doesn't matter how much stuff is actually between.
Right, I mean, you know, exactly. I mean, it's an uncountable amount of stuff in the unit interval, and there's also the same uncountable amount of stuff in the entire real line, right? These are the paradoxes of infinities, but they're not really paradoxes. They're just because we're not used to thinking about infinities.
Maybe just for convenience.
So maybe it's just for convenience. Well, I mean, and partly, but the other thing is like, I mean, mathematicians are pretty kind of retentive creatures, and like we make these not just for convention, but we hope they're rigorously defined. And you can actually kind of create your real numbers just out of your rational numbers by using this process of completion. And there, I mean, you have to go do an undergraduate level course in analysis, really. But
maybe you just solved up like calculus. No, just like draw like a square on like one of them, so square on another, and so this has a bigger area than the other one.
yeah, but you're still kind of getting away at the idea, because just as you said, right, there are just as many points in R2, right, the two-dimensional plane as there are on the line, right? You can have space-filling curves that visit everything, which can be put into one-to-one correspondence with just the real line. It's the same cardinality, right?
So then, Y is 2 greater than 1.
Y is 2 greater than 1. It's because we start out that way, basically, right?
But then we'll get something that's conflicting.
No, it's not conflicting. It's just, you can still, if you give me a number and another number, I can tell you which one's bigger than the other, right? That's not a problem.
But it's, okay, how do you define bigger? The amount of stuff that's in it, or like the...
What does that mean? What does like the amount of stuff in it mean, right?
Okay, like there's as many points between 0 and 1 and 0 and 2.
All right, but see, that's not a, yes, I mean, that's a true statement, but it's also true that there's, you know, as many odd numbers as there are natural numbers, right? There's as many even numbers as there are, you know, integers. Right?
But it's not a definite number, it's an infinity.
Right. Just as you said, it can be put into one-to-one correspondence with a subset of itself.
Like that picture.
Yeah.
But then, I just don't know how you can get from like things being that way and then you saying, okay, but this is still better than that one.
Well, yeah, you just don't use that as your metric for counting number of points because it's not a well-defined idea, right? I mean, it's well-defined, but it doesn't give you any info, right? What it would tell you is that the reals are bigger than the integers, right? But that's not, you want to know that 2 is bigger than 1, right?
So you just on like this number line, like put like a metric that's like almost the same as the integers on it.
I'm not sure, but if you want to know more about metrics and things, like we should talk about it after class. Just real quickly, can I field any other questions that people are burning deep down inside of them? All right, well then, yes, let's call it a wrap, and then feel free to stick around and hang out after class.
Even if you like explain like the self as like almost this data thing, how are you going to explain the observer of that data?
Yeah, it's a tangle hierarchy.
And even in then, you know, you have the observer, what the observer just observed, like being also put into the data. Okay.
They're not different from each other.
They're different or they're like the same?
They're the same.
Right.
They're not different.
So okay, you can say the data is observing itself, or it's
Right.
recording things about itself.
Because I mean, like even in quantum mechanics, you need an observer. Like the observer is just kind of really can be a measurement that just happens by the interaction of two particles. So the particles themselves can be kind of observers of themselves, right?
Quantum.
They kind of.
Did I say that?
No,
Quantum.
I was just thinking quantum mechanics.
Right.
Curran said.
Yeah, quantum. Okay, fair enough.